Hello viewers, I am Kausalya. Today we are going to solve problem number 3 under the topic lead compensator using Bode plot. The problem is design a phase lead compensator for the system shown in figure to satisfy the following specifications. So this is the system, right? Here the phase margin should be greater than or equal to 45 degrees and steady state error for ramp input is less than or equal to 1 by 15 and gain crossover frequency of the system is less than 7.5 radian per second. Right. So the step 1 is find K. Because you see in the transfer function we are having a constant K, right? So we have to find the value of K. So to find the value of K, the given data are steady state error is less than or equal to 1 by 15 for unit ramp input, right? So ESS is equal to 1 by kV. So when you rearrange, kV is 1 by ESS, and when you substitute the values, the value of kV is 15, right? Then what is the definition of kV? That is velocity error constant. It is limit s tends to 0, s into g of s into h of s. So s into g of s, the value of g of s is given in the problem and the value of h of s is 1 because it is a unity feedback system. So when you substitute the values, finally the value of kV is found to be equal to k. So kV is equal to 15, right? Therefore the value of k is also equal to 15, right? And step 2 is we have to draw the Bode plot for the uncompensated system. So this is the given transfer function, right? Just now we had find out the value of k. So just substitute the value of k over here. Then the next step is we have to replace s by j omega and this is our transfer function. So this is our transfer function, right? The next step is we are calculating corner frequencies. So corner frequencies are we have to take the reciprocal of the coefficient of j omega. Here coefficient of j omega is 1. When you take reciprocal again it is 1, right? And the next step is forming a table. So here our table has 4 columns: terms, corner frequency, slope and change in slope. So while considering term, the first thing is we have to include constant along with omega, individual omega. So here 15 by j omega. So write it first. Then the next thing is we are having corner frequency of 1, right? So this 1 is contributed by which term? It is contributed by 1 by 1 plus j omega term, this one. So second term I have to write like this, right? And the next thing is calculation of slope. So omega is in denominator, so it contributes minus 20 and here also minus 20. So the change of slope is a constant and individual omega won't provide any change of slope. So for calculating change of slope, this is I am moving this minus 20 downwards and I am shifting this minus 20 to the right hand side. So totally it is minus 40, right? And the next step is we have to choose 2 value of frequencies such that one value should be less than omega c1. This is our omega c1, right? This is our omega c1. So one value should be less than omega c1 and another one should be greater than omega c1. So select the values accordingly. So here omega L is 0.1 radian per second, right? Because we are having 1, even you can take 0.5 also, okay? Everything is right. And omega h is 10, even you can take 50 or 100, okay? Everything is right. And next we are going to calculate the magnitude for all these omega values. So here at omega equal to omega L, the magnitude is, it is given by constant with individual omega term. So in the transfer function again you see, we are having 15 divided by j omega, right? So just substitute over here. Since we want it in decibel, here 20 log is included. So substitute the value of omega here and finally calculate the value of magnitude, right? And the next step is at omega equal to omega c1, the value of a is, again you have to use the same thing. That is for omega L and omega c1, we have to consider only constant with individual omega term, right? So again substitute it over here and find out the value. It is 24 dB. And the next thing is at omega equal to omega h. So The formula is change of slope from omega c1 to omega h into log of omega h by omega c1 plus the value of a when omega equal to omega c1, right? So here what is the change of slope? Here you see I'm having this minus 40, right? And omega h value is 10. When you write it in the table, you will write like this. So change of slope from this point, that is this corner frequency to this frequency is minus 40, because here this minus 40 will be shifted downwards. So that is the reason here why we have written minus 40 here. So minus 40 into log 10 by 1 plus 24 gives you minus 16 dB. So just make a small tabulation, then it will be easy for us to plot, right? Next we are going to calculate phase plot. So phase plot is given by this expression. So again here you see omega in the denominator, okay, this contributes minus 90 degree, and again when you write expression this will be tan inverse of omega by 1. When you move this term to the numerator, then we have to include minus. That's it. Again for different values of omega, using this formula just calculate the value of phase angles, right? So the next thing is we have to draw the phase plot and magnitude plot on a semilog sheet. So you see this is our semilog sheet. The first step is we have to write the scale on x-axis and y-axis, right? So here I have started from 0.1, 1, 10 and 100, and in y-axis depending upon our magnitude value we have to select the things, right? And here this left hand side stands for magnitude, so here even you have to mention it as magnitude in dB, right? And here it is phase angle, so here you can write it as phase angle in degrees, right? It is must to mention these things, and you have to write the scale also. Here 1 unit is 10 dB and here 1 unit is 10 degrees, right? So the first step is we have to mark the points for Bode plot, that is first magnitude plot. So I hope you people know. So these are the values, right? For 0.1 it should be 44 and 1 24 and 10 minus 16. So let me show you how to mark 1 point, that is 0.1 44. You see this is our 0.1 and I have to mark the value of 44, right? So here this is 40, so this is 42 and this is our 44, right? Likewise you have to mark the remaining points. So I had marked them using pencil. You see here this point and this point. Now I am going to join these points using scale. Initially you have to connect these two, then these two. You see this is our Bode plot of the uncompensated system, right? Now we are going to draw our phase plot. So for phase plot you see here I had marked the angles, right? So as usual the value of the first phase plot is at a frequency of 0.1 the phase angle is minus 96. So again you see here lies our 0.1 and the value is minus 96, right? So you see here it is 90, right? So 92, 94 and here lies our 96. So to this line just with the help of scale, right, or by just counting from the 0 dB you can mark this. So this is our first point in our phase plot, right? 0.1 with an angle of minus 96. Likewise you just plot the remaining things. Again I have marked those points using a pencil, right? I hope it is clear. Now we are going to join these points using freehand. Wait, let me show you. So finally this is our phase plot, right? So this is our Bode plot of the uncompensated system, right? Now we are going to calculate the phase margin of the uncompensated system. So here we are going to calculate the phase margin. So how to calculate the phase margin? I don't want to draw too many lines, right? Okay. You see our magnitude plot crosses the 0 dB line at a particular point, right? When you draw a line from this point, it will meet the phase plot at some other point, right? At this point, just measure the angle, okay? This is found to be 167 degrees. Even if you get 1 or more degree, that is plus or minus 1. If you get 1 degree less or 1 degree more, it doesn't make much difference, okay? So here, the pi GC value is 167 degrees. So now we are proceeding with step number 3, finding the phase margin of uncompensated system. So with the help of our Bode plot, we had find out the value of pi GC as minus 167. So here what is the value of this gamma? This is given as 180 plus pi GC, that is phase margin. So here when you substitute the value of pi GC, the answer is 13 degrees. But the expected phase margin is 45 degrees. This is given in the problem, right? Therefore, we are moving to a lead compensation, right? Then the next thing is finding pi m. So here the desired phase margin is 45 degree. Okay, it should be greater than or equal to 45 degrees. So initially the value of epsilon is taken as 5 degrees. So what is the formula for maximum lead angle? It is pi m is equal to gamma d minus gamma plus epsilon. So when you substitute the values over here, the value of pi m is found to be 37 degrees. Step 5 is finding the transfer function of lead compensator. So here the value of alpha is given by 1 minus sin pi m divided by 1 plus sin pi m. So the value of pi m is 37 degrees. So just substitute it over here. And finally the value of alpha is found out to be 0.25. So when you want alpha in terms of dB, you have to include, that is you have to use this formula, minus 20 log 1 by square root of alpha, and the answer is minus 6 dB, right? So again we have to move back to our Bode plot. Okay, from step 5 we had calculated the value of magnitude as minus 6 dB, right? Therefore from minus 6 dB point, okay, this is 0, minus 2, minus 4 and minus 6. So from minus 6 dB, just draw a line. It will meet our magnitude plot. Just from this point, draw a line downwards. So you see here, the value of this omega m is found out to be 5.6 radian per second. So from the Bode plot, the value of omega m is 5.6 radian per second. So just substitute it in the formula. The t is given by 1 by omega m into square root of alpha. We know omega m, we know alpha. And finally the value of t is 0.36. So transfer function of lead compensator. So just substitute the values. And finally this is the transfer function of the lead compensator. Now we are proceeding with the next step, finding the open loop transfer function of the compensated system. So here you see, this is the transfer function of the uncompensated system, and this is the transfer function of the lead compensator, and this is the transfer function of the attenuation constant. That is, here this is 1 by alpha and here it is alpha into something, right? So this alpha value holds the same. And next we are going to find the open loop transfer function. Again, as we explained in the procedure, we are having 3 blocks in series. So just we have to multiply. So when you multiply here, we are having the answer like this, right? Open loop transfer function of compensated system. And the next thing is, again, we are going to draw the Bode plot for this transfer function, right? Hold on, take a deep breath, right? Now we are going to proceed again. So again, we have to use the same thing to draw the Bode plot. So the first step is we have to replace s by j omega. Then the next step is we have to find the corner frequencies. So how to find the corner frequencies? We have to take the reciprocal of the coefficient of omega. So here it is 0.36, here it is 0.09 and here it is 1. Right. First find out the values, then give the name according to the ascending order. Okay, that is the least corner frequency should be named as 1 and the next highest should be named as 2 and then finally the furthermost highest should be named as 3. Right. So the next thing is arranging the terms. So the first term should be constant with individual omega, right? And the rest of the terms we should arrange depending upon the corner frequencies. That is ascending order of corner frequencies. This is very, very important. Again, the next thing is slope. So omega denominator, so it contributes minus 20. Here omega is a numerator, so this contributes plus 20, right? And again this change of slope. So as usual, this minus 20 comes down and we are shifting this minus 20 to the right hand side, so it is minus 40. Again we are substituting minus 40 here and shifting this plus 20, so the answer is minus 20. And finally minus 20 is moved downwards and again this minus 20 is moved to the right hand side, so the answer is minus 40. So next we are going to find the magnitude for different corner frequencies. So as usual, select a corner frequency omega L which should be less than omega C1 and a high frequency omega H which is greater than omega C3. So here we have selected 0.1 and 50. Just substitute as usual. For omega L and omega C1 we have to consider only constant with individual omega terms. So here 20 log 15 by j omega. Likewise here at omega equal to omega C1 just substitute the values and calculate the magnitude. And again at omega equal to omega C2 there is a change of slope at omega C2. So just what to say, if I explain these things again it will take much more time. If you people have any doubt with Bode plot, just again go back to the normal Bode plot which we have discussed in, I hope so, in chapter 3. Right, so just look at the problems how we have solved that one. Okay, then it will be easy. So again as usual at omega C2 there is change of slope, so you have to use this formula, substitute the values accordingly. Again for omega C2 and omega C3 and for omega H as well, right? Calculate the respective value of the magnitude, that is the thing. And now we are going to frame a small table. You see this is my table which represents omega and their magnitudes. Next phase plot. So again we have to write expression for phase angle. So here a constant won't give you any phase angle and numerator I am having this term. So tan inverse of 0.36 omega by 1 and this omega contributes 90 degree. When I move this term to the numerator it is minus 90 and again this is a denominator term. When I move this to the numerator again there is a minus included, so minus tan inverse of 0.09 omega and here minus tan inverse of omega, right? So after writing the expression just include the values of omega. Okay, these all, it is good when you include all these values and as well you can also introduce the in between values. Okay, when you have around some 8 values of omega you will be getting more accurate phase plot. So just substitute the value, different values of omega in this expression and write down the values of the phase angles, right? And the next thing is again now we are going to draw this Bode plot, that is Bode plot of the compensated system, again in the same Simulog sheet. You see this is our Bode plot, right, which contains both uncompensated and compensated system, right? You see here this part, right, this part falls under compensated system. So this is our uncompensated system, that is these two lines uncompensated system, and here after compensation our Bode plot get modified like this, right? So this is the modification in our magnitude plot, and when you look at the phase plot you see there is a drastic change, right? Here these two are independent, you see. So this is the phase plot of the compensated system, whereas here this is the phase plot of uncompensated system, right? Now we are going to calculate the phase margin of this compensated system. Wait, let me zoom in. So again to calculate the phase margin, you see this is our compensated system, right? This compensated system crosses this 0 dB line at this particular point, right? Again just draw a line from this point till it meets our phase plot of compensated system. So when you draw a line using scale, hopefully this will coincide with this line, right? So you see, wait, let me draw using a scale. So when I draw a line, you see this exactly coincides with this line which we had already drawn, right? And this line meets our phase plot at this point, right? So just now measure the angle at this point. You see when you measure it is, okay, am I making things clear? You see, at this point, when you measure the angle, it is equal to minus 134 degrees. Right. So now we are going to substitute this phase angle in the formula. So now the value of this pi GC naught is nothing but minus 134 degrees. So here again substitute this in the formula. That is phase margin of the compensator system. Okay, that is denoted as gamma naught. So 180 degree plus pi GC naught. So here 180 minus 134 gives you 46 degrees. So here what is the expectation in the problem? You see the phase margin should be greater than or equal to 45 degrees. Right. So here what is the phase margin of the compensator system? It is 46 degrees. Right. So it meets the specification. Therefore, phase margin of the system is satisfactory. Therefore, the design is acceptable. Right. We can meet the specification. So it is good. Then the conclusion is over and the result, just you can mention the transfer function of lead compensator as well as transfer function of the lead compensator system. Right. So here comes the end of the problem. I know this problem is quite bigger. You need to concentrate more as well. So whenever you start seeing the video, just keep everything handy. Right. Then and there, whatever the instructions which are given, just follow. Whenever you do more practices, then it will be more easy for you to proceed. Right. If you have any doubt, let me know in the comment section. Thank you.